Welcome back, everyone. How y'all doing? So, my name is Emma, and for today's experiment, we are going to be doing some balloon geometry as a way to help visualize molecular geometry. And the best part is, the only thing you need this week are a bunch of balloons, and this will probably help you out some tape. Or if you don't have any tape, you can always just wind up tying the balloons together. So when I say a bunch of balloons, you probably need about 30 or so. There's a bunch of deflated ones, just regular latex balloons. All right, so what exactly is molecular geometry? Well, it's the arrangement of bonded atoms. Now, I know this may sound a bit confusing since we're talking about the super tiny atoms, and we both know that they're super complicated. Well, sometimes we need a little help with mentally visualizing things. So we can use a two-dimensional, or 2D, or three-dimensional, aka 3D, representation to help us. So for today's purposes, we are going to be using a 3D representation of molecular geometry. Why not use 2D, you're probably asking? Well, I'm happy you asked. So 2D visual representations of molecular geometry is predicted by the valence shell electron pair repulsion, aka VSEPR model, can be difficult to really thoroughly understand and to grasp the concept. So with 3D visual representations of molecular geometries, they actually help to give us the ability to view and manipulate our models with a direct hands-on experience. So this is really, really great for learning and retaining information. So it's important to understand the shape of a molecule for a variety of reasons, including, but not limited to, the melting point, density, and reactivity of a molecule as it's influenced by its shape. All right, so with that being said, the objective of today's experiment is to gain a better understanding of molecular geometry by making a 3D visual representations and manipulating them with our hands. We're going to be discussing a whole bunch of different electron domain geometries, about 24 today. And for each of the 24 electron domain geometries, we will indicate 5 things. We will indicate the total number of electron domains, number 1. Number 2 is the type of molecule. Number 3, electron domain geometry. Number 4, number of lone pairs. And number 5, an example. All right, so as I mentioned, you're going to need a bunch of balloons for today's experiment. Go to the convenience store, grocery store, or wherever you want to buy balloons, just grab a bag. How I said, you're going to need a lot, probably around 30. And then you're going to want to inflate them. You can blow them up. You can use an air compressor like I did. It's a lot easier. And then when you're done, you're just going to tie them at the end to secure them. As you can see, I already did that ahead of time. Here's a whole bunch of balloons that I inflated and tied off on the end just with some knots. Okay. So let's go over some of the basics of molecular geometry, just to get a gist of it about what we're going to delve into with those 24 examples that I mentioned earlier. Okay, so here we have an example of a linear geometry in which there are 2 electron domains and 0 lone pairs. An example of this would be carbon dioxide, aka CO2. Okay. Next, going one up, we have trigonal planar geometry with 3 electron domains among lone pairs. An example of this would be sulfur dioxide, aka SO2. Building on that, we would have tetrahedral geometry with 4 electron domains. An example of this would be methane, aka CH4. And then building off of that, we would have trigonal bipyramidal geometry with 5 electron domains. An example would be phosphorus pentachloride, aka PCl5. And then building off of that, we would have octahedral geometry with 6 electron domains. An example would be sulfur hexafluoride, aka SF6. Great. So let's jump into the examples that are on table 9.2 of our textbook. All right. So our first example right here is a trigonal plane. The balloon's figure electron domain geometry is trigonal planar. The total number of electron domains is 3. The type of molecule is AB2. The number of lone pairs is 1. And the placement of the lone pairs is right here, would be right here in the middle where they're all connected. Right there. It has a molecular geometry that would be bent. An example of this would be SO2, aka sulfur dioxide. If you're wondering what sulfur dioxide is, it's a smell of burnt matches. It's a really common air pollutant, and it's released in the atmosphere most commonly via the burning of fossil fuels by power plants and other industrial facilities. Once again, here's our card with our info. All right, moving on to our second example. Okay, so the next one of electronic domain geometry example is that of a tetrahedral. The total number of electron domains is 4. The type of molecule is AB3. The number of lone pairs is 1. And the placement of the lone pairs would be right here in the middle of them. It has a molecular geometry that is a trigonal pyramidal. And an example of this would be NH3, aka ammonia. So you might be familiar with ammonia. It's pretty common in a lot of household products, but it has a variety of uses, from being used that of woodworking, to cleaning, to being used as fertilizer, as stimulant, and a variety of other uses. You're most probably familiar with it being used in Windex and other household cleaners, but most commonly Windex, especially the older formulated version. It had a higher concentration of that ammonia. Once again, here's our card. Okay, so for our next electronic domain example is also a tetrahedral, but this one's a little bit different as its molecular geometry is actually bent. All right, so to switch things up a little bit so we can have a better visualization, I'll be using this one as an example. Okay, so we have the total number of electron domains is 4. And the type of molecule is AB2. The number of lone pairs is 2. And the placement of the lone pairs is right here in the middle, but a little bit skewed. Right around there would be these places. So 2 on each side. Oopsies. Okay. So it's important to note that in this example, the molecular shape is actually bent. This is because when you have this shape and you take out 2 of the balloons as lone pairs, so let's say we take out the orange and black balloons, they actually wind up bending these 2 other balloons, the yellow ones, downwards, so that the yellow balloons would be bent downwards at an angle. And so the molecular geometric shape that arises would be bent. That's if there's lone pairs within this family. Now, example of this would actually be water. So now, for our next electron domain geometry example, it's a trigonal bipyramidal. It's 2 triangular pyramids on top of one another. Basically, we're going to take the tetrahedral that we had used previously just a moment ago when our example was water, and we're going to add a balloon to it. So you can see right here. So it actually shows the 5 lobes of electrons to the 4 orbitals shown previously in the tetrahedral that we had made just a moment ago before this. All right, so when we do that, we actually wind up with a stable structure. We have our axial positions, the yellow here, with a bond of about 90 degrees, and equatorial positions, these, the non-yellow balloons, 3 going around, with a bond angle of about 120 degrees. Combined together, they form the trigonal bipyramidal, and it's shown expanding octets. Okay, so the total number of electron domains is 5. and the type of molecule is AB4. The number of lone pairs is 1. So what actually ends up happening is, let's remove this one right here, because this is where the lone pairs would be, in this position right over here. So the number of lone pairs is 1, and this will result in a seesaw. The lone pair occupies one of the equatorial positions, as the orange balloon that I had just removed, making the molecular geometry a seesaw shape. So the placement of the lone pairs, as I mentioned right here, is where the orange balloon was just a moment ago. And it has a molecular geometry that of the seesaw shape is mentioned. And an example of this would be SF4, aka sulfur tetrafluoride. If you're curious what that is, that's a colorless gas and it's pretty corrosive. Some applications include for the preparation of organofluorine compounds, such as fluorocarbons, amongst others, and some of their uses are that in pharmaceuticals. Just real quick, a brief summary of what we had just discussed. Looks like that. Pull that away. 1 electron's right there. Next thing you know, we have a seesaw shape. Moving on to our next example. This one is also falling into the same category as the last one, trigonal bipyramidal, but this one is T-shaped. Okay, so let's just start over the basics. Quick summary. The total number of electron domains is 5, and the type of molecule is AB3. The number of lone pairs is 2. Now, the placement of the lone pairs is both on the equatorial axis, meaning going around. You're going to remove one, and one of the lone pairs will be here. And remove the other one. One of the lone pairs will be there. That accounts for 2 of the lone pairs. As we can see, the ending result is that of a T-shape. So it has a molecular geometry of T-shape. Now, an example of this would be ClF3, aka chlorine trifluoride. If you're wondering what that is, it's used as a cleaner in the semiconductor industry for chemical vapor deposition chambers. And previously, it was being investigated as an oxidizer for rocket fuel and rocket-propelled systems. Unfortunately, that didn't really go anywhere due to its high level of danger and it being quite toxic. So the last one for this electron domain geometry. For this example, it's the same as the last two, trigonal bipyramidal, but the molecular geometry of this one is linear. Okay. So, just some quick overview of it. The total number of electron domains is 5, as were the last two, by the way. And the type of molecule is AB2. And the number of lone pairs is 3 total. Now, it's important to note that the placement of the 3 lone pairs that are in this example occur all along the equatorial axis, or around. Okay, so the bond angle is actually going to wind up being 180 degrees. So I'm just removing these to show you where the lone pairs will occur. Here, here, and here. As I mentioned, the bond angle will be 180 degrees. So an example of this would be XeF2, aka xenon difluoride. What's that? Never heard of it? Well, you might have if you worked in a lab, or if you're familiar with electrochemical procedures. It's a white crystalline solid that's commonly used for fluorinating purposes in electrochemical procedures as well as laboratories. Let's wrap this up with the final 2 balloon models that we're making today. So, electron domain for both of these is called octahedral. And in this family, the lone pairs are always in the axial position, meaning up and down. This is for stability purposes. Now, within this family, there are 2 different molecular geometries: square pyramidal and square planar. Let's start with the first one, square pyramidal. All right, so the electron domain geometry is octahedral, and the molecular geometry is square pyramidal and has a 90-degree bond angles. It has 6 pairs of electrons surrounding a central atom, therefore indicating that it is an expanded octet. Here is some information detailing that. The total number of electron domains is 6. The type of molecule is AB5. The number of lone pairs is 1. And the placement of our lone pair actually occurs along the axial position, meaning up and down. It would be the red balloon and the black balloon in this case. Example of our octahedral. So, in demonstrating the square pyramidal, we are just going to show where the lone pair would bind. Actually bind right down here in the base of it. Just remove this and there. So, an example of this would be BrF5, aka bromine pentafluoride. What is that, you're probably wondering? Well, it's a colorless liquid that's mainly used as a fluorinating agent to produce fluorocarbons, and also as an oxidizer, mostly in rocket propellant systems and uranium processing. All right, so let's move on to the second one, the square planar. So this one is also in the octahedral family, and it has a molecular shape called square planar. Octahedral family, as you can see, there are 6. 1, 2, 3, 4, 5, 6. Now, the total number of electron domains is also 6. It's made up of 6 equally spaced hybrid orbitals arranged at 90-degree angles, same as the one prior to this. The type of molecule is AB4, and the number of lone pairs is 2 in this case. Now, the placement of lone pairs occurs along the axial position, as it does with the octahedral family. So, let's move some around. The reason why the lone pairs occur in the axial position is for stability purposes, as these lone pairs are on the central atom in the molecule. I'm just going to show this to you guys. So we're removing one, lone pairs, and let's remove our second one. There. So as you see, I removed them along the axial position, which was pink on top and then orange. Remove them, and we're left with this. So a pair would be attached here, another pair would be attached there. So it has a molecular geometry that is square planar, and it has bond angles of 90 degrees. This is a result of the molecule's 4 bonded atoms and placement of the 2 lone pairs, as mentioned, along the axial position. So up here, and then down here, which I just removed. Now, an example of this would be XeF4, aka xenon tetrafluoride. What is this? Happy you asked. Well, it's an inert, colorless gas, and it's mostly used in metal purities to find them in silicone rubber to help ensure its quality. All right, well, that concludes this week's fun example of a whole bunch of balloons. As you can see, we had so many. I hope you had fun. And if you have any difficulty with this, just comment below, and I'm more than happy to help you out or to answer any questions you may have. Thank you.